Good evening, everyone, and thanks a lot for traveling through the very cold weather tonight and come to our talk and listening to AI. My name is Raymond Ang. I'm from Emotech, and this is Emotech. We are a group of people with diverse background covering AI, neuroscience, speech technology, computer science, and design, animation, etc., engineering. We are creating the robot, Ollie, and today I'm going to focus on speech technology. I'm one of the research scientists in acoustic and speech science, and when we talk about speech technology, we can think about the typical application of speech recognition. We take out our mobile phone, talk to it, the voice got uploaded to the cloud, then there are some phonetic symbols being transcribed, and finally it returns to us as a bunch of meaningful text. Today I'm going to focus on these tiny little phonetic symbols in speech recognition. I'm trying to contradict myself. I try to go into as much as details as possible, but not as too confounded or too complicated that we can easily grasp the meaning of speech technology. Currently, we know with deep neural network and deep learning, things got so easy. You can just download TensorFlow, use carriers, and build your own machine learning models. But these do not come for free. It builds on the success of many different researchers from the past, from many different fields. Here, I would just like to highlight one of the many very hardworking and academics who contributes to the field. A British linguist, Peter Leckevoogd, who has father from a Danish father, and he spent a lot of time in UCLA, America, doing field linguistics. Many people think linguists are leading an easy life and they are very theoretical, just sit in the office, but definitely it's not the case for him. He traveled around the world. He's a field phonetician, collecting a lot of data and tried to understand how humans pronounce speech in terms of physiology and also the mechanisms behind. In one of his personal notes, he highlights the importance of having a group team to work with. We know this is always true, but then when I look at his work and his research, I kind of have an alternative interpretation of that. One of his studies is about how do we produce sound from our lung and our vocal tract. Currently, with the modern technology, we have X-rays, we have MRI, it's very easy to conduct non-intrusive study to know the details of the physiological mechanisms. However, what he did at that time in the 50s and 60s, he gathered himself, of course, and also his group member, turned himself upside down and inserted a tube-like apparatus down to his throat to measure the volume of the throat and also lung pressure. What's more, in order to measure the intercostal muscle, which are the muscles between ribs, the pressures of these muscles, he tried to use a very sharp needle, pinch into his chest, and then he don't use any pain relieving medicine because he has to keep track of the actual measurement. So these are the real pain and efforts our fellow academician went through before deriving the very small graphs of lung pressure along the time when we speak about R. So I think these many little stories deserve their credits towards the way or towards where we are now, which is a very handy platform on learning different stuff, mapping data, making sense of it, and also using it in a very convenient way. So I said already in the beginning of the talk, I'm going to go a little bit into the details. So when we talk about speech technology, there are of course a bunch of applications we can think of. Speech recognition, voice recognition, decoding your speech to text. And also you have speech synthesis. Google has currently Wavelet, which synthesizes human-like voice with very high naturalist degree. And also we have voice print authentication, using your voice to try to identify your identity. And also language identification, using the voice to detect the language which is being spoken. But now, from now on, I'm going to focus on one particular bit in speech technology. I'm trying to make sense of it and hope I can bring you some insights on this. We start with phonemes. So this is the very painful but interesting valuable graph of phoneme production. And this is another perspective of phonemes in the signal processing dimension. If you know a bit about signal processing, you know Fourier transform by transforming your signal to the frequency domain, just like what you have in your hi-fi. So you have high frequency bars and low frequency bars, which visualize the quality of different frequencies of your audio. So this is what it is. We record some of the sounds from the speech production, transform it to the frequency domain. In the x-axis, you can see the frequency from low frequency to high frequency, and then these are the relative strength of different components of it. Phoneticians and also signal processing people, they study a lot of it, and they derive a rule to map these physical quantities to the actual vowels or consonants we produce. To be able to speech is actually a very complicated mechanism which go through inside our body. First, we have to sustain a very controlled manner of exhalation of air from our lung. So we cannot just blow out the air in an uncontrolled way, because then our voice cannot sustain. And also we have to constrain our articulation organ in very particular way, for example our lips, our teeth and our throat, so that there will be different resonance pattern. Just think of a flute or just a windpipe. When you have different shapes, then resonance pattern differs and you hear different sounds. And that's the reason behind. When we look at the frequency spectrum, we see the high frequency regions, which is called resonance regions. We can do a low pass filter to trace the general tendency of these magnitude. So the first peak of the resonance, we call that the first formant, and the second peak, second highest peak, second lowest peak, we'll call this the second formant. With linguistics analysis, we know that with these many different phonemes, they exhibit actually different formant patterns. A low first formant, which is a formant with low frequency, correspond to high vowels, which are in the region E, U, where, if you can imagine, the resonance region is far up in the mouth. This is as contrast to other low vowels such as R, or where your resonance pattern is low there. So these all different patterns, physiological patterns, can now be perfectly correlated to these formant frequency, and now we have a way to measure the phonemic categorization from the physical measurements of sound. So this is another perspective in a more engineering visualization, again about speech recognition. So we have the voice there in the far left, and then it is decoded into the phonemes I have shown there. And in the end, we have the complete string of words. There is a sequence of complicated process which I'm not going to go through in details. Again, I'm going to highlight phonemes and how it's mapped to the physical output of sound from our mouth. We have a mathematical model which is based on statistics and probability. Basically, we are computing the probability of a given sound observation and to see what is the word which gives us the higher probability. If you know a bit about probability theory, Bayes' rules is frequently used in probability calculation. We break down this probability into two parts. The first part is about the probability of the sound, and we build some models of the words to generate the sound, and this is what we call the acoustic model. And I'm going to talk a little bit more about acoustics model in the classical theory of hidden Markov model and also deep learning. There are some basic assumptions of statistical theory. This is particularly important in the classical framework that we're talking about Gaussian mixture model or hidden Markov process. We look at the short time stationary properties of the signal because at the end of the day we're trying to build mathematical model which describe things which are well defined. If we use a mathematical model to cover a very long chunk of data, then we lose the stationary property and the statistics will be very hard to describe. So first, we look at the signal in different short time frames. Here we are talking about a time resolution around 20 milliseconds to 30 milliseconds. There we extract the signal and we assume the property of the signals are stationary and can be described by relatively simple statistics. And then there are latent variables. The idea of latent variable can be explained like this. And now I want to describe a sound R, and I try to build a model with R with many different data. But we know in the real world, different people under different circumstances, they pronounce R in a different manner. So even within the single model R, there will be different representation, and there cannot always be very clear mapping between model and observation. So there's a very clever way to try to split the data into different subparts and to correlate these data into each of the subparts depending on the similarity of the data. So here now it is a data-driven process. We let the data speak instead of hard classification of these data, and it does brings us benefits in modeling. And then with these simple assumptions, we try to build, using the graphic model theory, a hidden Markov model. Now I'm going to use another analogy to explain to you, which I hope it will be intuitive. Now, going back to the scenario of describing sound from model, think about having cassette tapes or audio tapes. So now you have a task of describing the sound R, and you are given 3 audio tapes. And it doesn't matter which audio tapes you use. You use any of your 3 audio tapes to record your sound R. And in the audio tape, it is infinitely long or with a very long duration. Then you can put in a lot of different examples of these R in the audio tapes. What this model is doing is trying to look through the time when we produce R. I talked about the temporal resolution being very short, so it is around 20 milliseconds. So within one instance of R, we go through a lot of these states. In each of the states, we try to pick a random audio tape, which will record the realization of the sound R. It doesn't matter what it takes, as long as those examples who put into a single tape will be consistent enough that we can effectively model these sounds. So we have now the tapes here. We randomly choose different tapes in different states or in different steps. When we are inside the steps, we try to put the tape into an audio player and do a fast forward or backward operation to a random place to play sound. And this is the mechanism of generating the sound. The task of modeling phonemes or speech recognizer depends on how well you make your audio tape and how well the process of randomly choosing different audio tapes and different positions of the audio tapes works for you. The better your mechanism or your setup describe the audio, then the better the model quality it will be. So this is just another visualization of this audio tape example I gave. We talked about transversing through the random sequence, the time sequence, and playing random tapes. In each of the sequence, we just choose different tapes. So there are n different steps here, but I told you there are actually only 3 tapes. So there will be a question of which tape am I going to choose in this sequence and which tape am I going to choose at that second steps. We use another probability process to try to map this sequence. This is called an automaton. And then we try to link different states, which means what is chosen in this time instance actually has some correlation in the last instance. So think about a little bit to the real examples. When we try to truncate our speech example into very short segments, these short segments are not actually independent. They actually correlate with each other because they are so close together. So this is the link between different states in time, which we model, and to provide the smoothness and the coherence of the outputs we are having here. For more technical details, I'll refer you to Rabinowitz. This is a very classical work that every one of us working in speech technology or machine learning or even other useful example in HMM like gene modification, we all recommend this tutorial study. But you may have a question, why am I spending so much time talking about technology 30 years ago? What does it have to do with deep learning? Everyone is using deep neural network. Forget about all the hidden Markov model, Gaussian mixture model. You will see the reasons why. But first, let me just jump. I think many of you, or some of you at least, may be very eager to listen to this part already. I'm not going to give you a very sophisticated neural network example, but instead I'm going to quote a very classic exclusive SOR example to explain why neural network will help in the classification task. The task we are having now, putting this into context, we try to be consistent. We have only a very short time window, 20 milliseconds, and this is a sound. And we are going to classify this sound into one of these phoneme categories. This is a classification problem. We start with a multi-dimensional feature space where we describe the sounds. It doesn't matter what features these are. You can just consider that as a bunch of numbers taken from our measurement. And then we have different categories. Here there are two classes. It can be the class of a phoneme R and a phoneme E. It doesn't matter what class this is. Now we have a quite difficult problem in the exclusive SOR in the way that when we look at the examples of two classes here, you can see the classes kind of intersect with each other, that we cannot derive a very clear linear hyperplane to separate the two classes. If we have a more easier case, then we would have expected class 1 to lie on the left side of the hyperplane and then class B lie on the right side of the hyperplane. Unfortunately, this is not the case. We can use a lot of different fancy algorithms, SVM, kernel, to have nonlinear hyperplane to separate these space that we want to classify. In the neural network or multi-layer perceptron solution, what we do here is we try to propose two logic gates. First, we have an OR logic gate. This is taking two inputs, one of the inputs from the x-axis and one of the input from the y-axis. We just add them together and we pass through a squash function, which is an activation function in neural network. So this linear transform is represented by the linear plane here, and then the squashing function is represented by the way that it just accepts all the values above this hyperplane, which is the upper half plane here. And then we have another logic gate implementation, which is a NAND logic gate. You can have the same weight gradient here, which is represented by the line with the same gradient. And then you propose a different activation function which actually accepts only those values which are lower than the transformed value. So here we have two very simple neurons producing an OR and a NAND logic. And here comes the magic. We have another layer of the neuron which combines the output of the 2 logic gates, so that if we take only the outputs of the plane above the green line and also the region below the purple line, then we can exactly model this particular region of exclusive OR. So this is the very basis of deep neural network, because if you imagine, if you put more and more neurons in your first layer, then you can draw more and more lines, and these unlimited straight line eventually can link up into any nonlinear curve which describe your feature space. And then you can add it up multi-layer, which means you can assume different combinations of these curves to achieve whatever decision boundary you hope to. So this is a really very clever way of implementing classification and learning decision boundary. It was proposed back in the 1980s. There has been a really very competitive time when that was called artificial neural network and the hidden Markov model just were hand in hand. But at that time, computation power was limited and there was not a clever training algorithm which can help us solve this problem. But now we are in the place we have all the hardware algorithms ready, so that's why this deep neural network technology just fly off in recent years. Again, there are 2 readings that I would recommend for speech technology in deep learning. Of course, we go to the IEEE transaction in 2012, where IBM, Google, Microsoft, and University of Toronto, which is where Jeff Hinton is from, they study deep neural network advanced. The field moved so fast, so there are some of the practices which are described in the 2012 reading which are no longer true. People no longer follow these. But still, I think this is a very good and comprehensive overview of the whole technology. And of course, there's a Nature article from Yannick Kuhn in 2015, also talking a bit more about different deep learning training strategy. With all different advances of deep network, deep learning, we see actually exponential growth of performance in terms of accuracy and also complexity and also running time of model. To highlight a bit, there are enhancement in training. So there are sequence training, which is a kind of a discriminative training in neural network. It comes into place around 2013-14 and improves the neural network performance. Dropout is a very strong regularization measure by omitting some of the weight in the deep neural network in training to prevent overtraining. There are other methods or mechanisms of improving training efficiency, for example, distributed training, etc. And these all help to improve model efficiency and also performance. Convolutional neural network, recurrent neural network are 2 of the very new architecture of network which was not conventionally used in neural network in speech recognition, but now it is being considered more and more seriously in our training. And of course, recently attention end-to-end training allowed us to improve the model performance even to another degree. To highlight how these different techniques gives improvements to the speech technology, we use we like to use empirical data sets and run experiments which is comparable and repeatable, so that we can have benchmark results to judge the efficacy of each of the proposed technology. So the GMM HMM method gives us word error rates in a typical well-used conversation telephone dataset at an error rate of around 23%. This is at the time around before 2010. So with the start of the introduction of DNN, we have already a sharp decrease of error from 23 to 16. So in academia, normally if we have a relative improvement of 10%, it is considered significant. So if you jumped from 22 to 20, this is already a huge jump. Then you see the big advancement here. Then it comes to adaptation and sequence training, which is the discriminative training I mentioned. It gives a further 20%. Then convolution neural network, and this part and also the number at the bottom is about model combination. We know for a very long time that by combining different models, the performance of different systems will improve significantly. So this comes at no surprises. In Emotype ourselves, we also are very serious in the performance of our speech technology. So we run a benchmark experiment to compare our model to different state-of-the-art technologies. This is two of the experiments we want to highlight. We run a speech recognition in a very small test speech recognition task with around thousands of words. We compare that with our in-house ASL system to the Google API. We got very comparative results, standing at around 10% of our error rates. We also have the speaker recognition capabilities to recognize different speakers in the home environment. There we have 6 speakers in the group, and the machine is learning enrolling the speaker with a limited amount of speech at around 20 to 30 seconds to learn the speaker identity and then recognize its identity. So we compare our in-house system with the Microsoft Azure speaker recognition API in January, and we got a significant improvement above the compared with the Microsoft system. Having said that, I also want to highlight the way we interpret these different numbers, because we are always presented a lot of numbers, word error rates, performance, and sometimes it's really very difficult to judge, because it doesn't make sense at all if we are told that Microsoft speech recognition system achieve human parity or human accuracy, but at the same time we see an experience from a Spanish-American family when they ask about a song. Hey computer, can you play K, etc. And some of the embarrassing results just comes up. So this is of no surprise, because in this particular example, this is because of accents. We know that machine learning system has to be trained on data, and it depends on what data you're going to use to train your system. Then your system will be biased to different conditions. So just name a few of different conditions. Audio sample rate will definitely change the quality of the machine learning system. We see a consistent around 3% absolute accuracy degradation when we lower the sampling rate of the audio. So this is universal across different tasks, no surprise. But when we play different sounds with different sampling rate to people, we never see this accuracy degradation. So this is something which we really have to take care of, because we can't take it for granted that machine is learning like human. There are still some of the difficulties or mismatch that we have to tell the machine to explicitly adapt before it can do it for us. Front-end processing, we highlight some of the sophisticated system with very low word error rates. Actually, when we dissect the system, we can see a lot of different front-end calculation, transformation, computation, which takes a lot of time in doing denoising, variability adaptation, etc. Acoustic noise, channel, reverberation, distance from microphones. So these are about the background or the conditions of the inputs. To human, these variations in conditions doesn't change the intelligibility of the voice, but it does change a lot in terms of system performance. Domain. So when we talk in a very serious context, in news or in a very formal speech, machines tend to be easier to understand, just because it is mostly trained on these kind of data, and then there are abundant amount of good quality data in this domain. When we moved into different domain, for example, conversational speech or even colloquial speech, machine will have a hard time if we have not give enough data to bias the learning of the machine. Of course, there are counterexamples, particularly in recent years when we talk about meta-learning, learning to learn. We are starting to develop machines which have the ability to generalize and learn very fast with very limited of data. But in the commercial setting, if we look into across different applications, with all requirements on, for example, runtime, model complexity, we are not there yet, but we believe we are moving closer and closer towards having the machine being more flexible. So this is the whole picture of performance. If we want to quote speech recognition accuracy, for example, we always love to put things into context. So one single number of 5% normally doesn't make sense. We normally like to put all the data in different conditions all together. So in the x-axis, you can see it is the axis along the time. So naturally, we are progressing in terms of word error rates. We have lower and lower word error rates along the time when we advance our research. But then we can see different tasks. So we have read speech, which we put people in front of microphone and read a passage very carefully. So they read it correctly, without accent, without any pronunciation mistakes. So it is a relatively easy task. And then we have a second easy task in air travel planning kiosk. This is some air traffic controller in an air traffic workplace, basically. So their vocabulary is limited. It is command-based because they have to have very effective communication with the pilot. So these are, again, quite predictable and easy tasks to work with. And then we move to broadcast speech. We have switchboard here, so this is the data set which I just shown you with one of the large green tables in the earlier slides, where we stood at around 20% of word error rates in the 90s, and then we are now down to around 5%. But even if we have 5% of the switchboard data set, we still have a particularly challenging time with meeting speech, for example, when people overlap their speech when they are inside a meeting room, and in most of the meeting room we have heavy reverberation. Also, people don't wear microphones close to their mouth. The microphones are far away. These are all the factors which degrades the performance of speech recognition system. And then there are the conversation telephone speech. This is a bit easier than meeting speech, and then we are also making progress along conversation telephone speech area. So to conclude my talk, I was trying to introduce the subject matter with examples of phonetic units and try to explain to you how we can model that from the very primitive way of inserting tubes into our throat to measure the accurate physiological measurement, to some classical mathematical model, hidden Markov model, towards deep neural network in the state-of-the-art technology. Then we try to look at also system capabilities and some of the performance analysis that I was and I am always repeating myself to try to put these numbers into context and interpret that in an appropriate way. In the end of the talk, I also want to highlight that we are hiring. So if you're interested in working with us and also tackling this very challenging problem, talk to Julia, our Human Resource Officer Manager, and also Diogo. Maybe he will be able to give information on us. So this is the end of my talk. Thank you very much.
Thank you very much, Raymond. And just to check, are there any questions? Lovely. We have about 5 minutes and then we'll hand over to the second speaker.
Thank you very much for the talk, very informative. How long until the API or the SDK is ready, please?
Sorry, wait. We are equipped for this.
We are planning. I can't give you an exact date because we are planning about how to effectively manage that. So the complication will be we want to try to make it as flexible enough, but at the same time like user-friendly enough, so that can create the most synergy. But that will be, we will give more information in the coming months because I assure you planning has been already undergoing.
Thank you.
Thank you.
Great speech, and I love Ollie, by the way. As a dev, we have a small community in London, and are there any platforms or anything ready for us to actually try to do API calls now, like a sandbox or something?
Yes, I think what is that is a really interesting idea, and then I'll definitely find you offline and then talk more onto that.
Hi. Do you see any future beyond phonemes? Like I see WaveNet for speech synthesis. They don't actually operate on phonemes. They operate on sounds that don't really make any sense. So do you see any future beyond using phonemes as the unit for modeling?
Yes, thank you. That's a good question, actually. Right, WaveNet and also other end-to-end training are many of the examples where researchers are trying to bypass the traditional or classical linguistic structure in learning. And this is actually quite promising. We see some of the results there. One of the barriers there or hurdles there are the huge complexity of computation when we throw away the formal structure. We knew it was the case for WaveNet. It's no longer now, which is the huge computation time it takes to generate the very high frequency outputs there. But then again, with more engineering power, then they are making a huge progress. And also there are Tacotron, which look at the spectral content instead of the temporal content of the wave. So there are actually different ways if we look at the data-driven approach. But to stick to the context of this talk, perhaps I would also advocate the importance of classical knowledge, particularly in application-driven research. The reason is that if we know a bit of the classical theory and also the structure of the model, then it saves us a lot of time and also space complexity when we build the model. Then it will have a lower entry barrier for us to have a state-of-the-art performance to start with.
That was one of the things.
Can you speak about the privacy concerns, if at all, and how we are handling that?
Okay. For privacy, speech application is one of the applications which draws privacy concern. We have some of our modules, for example, the voice trigger and speaker recognition, which operates completely offline, so it doesn't involve any streaming. and the data won't be stored into on the cloud or anywhere. So privacy is fully protected. And on top of that, actually we do like feature extraction and encryption. So it's very difficult that we can reconstruct the signal. There are other concerns. We know generally as a community, EU is very concerned on that. So there will be EU law on privacy, which will be rolled out in the middle of this year, and we are fully comply with that. There will be all the formal structure in our work and also in terms of our human resource management, which particularly look into this issue.
And also, actually, on Facebook, you can find Oli Robot this page. We have very special details about all the privacy concerns. Yeah. Welcome to follow.
Thanks.
Two more and then on to the next speaker. You can always grab, I think, either of you two after for more questions.
Where can I buy Oli? I mean, been looking for it for a year.
Sorry?
Where can I buy Oli?
Yeah, so I think we have announcement in Indiegogo. So we are pre-selling Indiegogo, and then we're going to ship this in the early mid-summer. So, but we'll keep on update. We have very frequent update in Indiegogo on our production status, and I think we recently showcased some of our applications in integration, and if I remember correctly, there are some machine learning models that we want to highlight as well, which are the real demonstration that exhibit the error rates, state-of-the-art error rates that we achieved.
You still can pre-order through Indiegogo platform, but you miss the best price.
It's too expensive for me. I've been on your site and I'm not that rich.
I assure you it's worth the price.
Okay, do we have any final question? Otherwise we'll move on to the second speech. Okay, fantastic. So thank you very much, Raymond. Yeah, and this will be Sean giving us his presentation. Thank you.
Hello everyone, so I'm Sean Wen, so you can call me Zhongxian, that's my Mandarin name, but usually people just call me Sean because the name is actually very hard to pronounce it. So you can try, but if you just call me Sean, that's also fine. I get used to it already. Yeah. So we are a fresh new company, a new startup. We just founded last year, end of last year. So we are called Poly AI. So the goal is that we want to make a conversational agent that can operate across different platforms, different languages, and also different domains as well. So today's topic is called Democratized Conversational AI, which is happen to be the main mission of Poly AI as well. So I will talk a little bit about. So we are basically a bunch of Cambridge PhD students who went out and started the company, and we hired a lot of good people. And then we are going to share some of the. So we are trying to apply our research to industrial application, and along the way we actually learn a lot of these lessons when you try to apply research to industrial applications. What are the pitfalls you need to pay attention to? So basically, I'm going to just here to share all these lessons we learned. So basically, before we started, let's get back to the history of the technology evolution. So this is what we are going to talk about specifically for information technologies. So in the early 1876, when Bell first invented the phone, we firstly have the first chance to actually talk to a person remotely. So we can actually access services remotely, like you can book a restaurant, you can book a delivery or things like that. So this is actually very useful technology. And the second iteration in 1989, we have the World Wide Web. Then nowadays people use Google search engine, Microsoft Bing all the time to search all the information you need. So this is another very important evolution in this particular information technology. And the third thing that happened in 2007 in January. So when Apple first launched the iPhone. Right, so then now everyone has their own smartphones, and you can download a lot of applications, and a lot of developers are building the community So you can actually use a lot of good apps just in your pocket, and you can have a lot of services just stored in your pocket. And the current iteration we've been through is so-called chatbot. So Facebook launched this messenger chatbots and started the era of conversation AI. But apparently this chatbot is not getting traction yet because a lot of people find that it's actually an interactive app crammed in your messenger. So it's actually not a conversation AI at all. So what we are looking for is exactly like both Polyam and Oli are doing here, is that we are aiming for the next era of the technology evolution, which is the era of virtual personal assistant, where you can actually just use a voice to access it, and there are quite a lot of skills. For example, Amazon have launched a lot of Alexa skills, and then Google Home is also have a lot of actions as well. So you will also build a community around that. So imagine in the future, you can just use voice to access any kind of services you want. Right? So that's something we are actually looking for in the next iteration. And now you can see that the industry landscape that quite lots of these chatbot building companies and conversation AI companies in the past 2 or 3 years. But you can see that some of them has been ASIC and some of them are still there. But most of these companies are trying to build a flowchart dialogue system design. So basically it requires you as a developer to sit down and write down a whole bunch of rules and a whole bunch of dialogue flows that actually leads the user to the end. And so this is a very simple conversation, try to book an Uber. So you actually need to write down all the possible ways that user may probably want to say about booking an Uber. And you need to distinguish whether the user want Uber X or Uber Black or things like that. So you can see that this entire thing is apparently not very scalable. So the things that why we can do better is that because, as I said previously, we have a lot of people from the academia background. We have been research in this particular sector for a very long time. So these are the papers we published for the 5 of us in the past 6-7 years. So we have language understanding, dialogue management, natural language generation, and neural data modeling. So that's why the 5 of us think that it's actually good for us to start this Poly-AI to actually help us to help the community to speed up the building of the conversation agents. So we are going to use our domain knowledge to actually make these things happen. So this is today's outline. So firstly, I will talk about the conversational AI general architecture and why we use machine learning to solve it. And then some of the pitfalls I want to, when we apply research to products, like some of the pitfalls you should avoid, and then finally the conclusion. So this is typically the conversational AI architecture people build. So basically, this is a spoken dialogue system. So we will usually break it down into 5 different modules. So in the beginning, you will have these 2 speech modules that talk about in the last talk. You have speech recognition to convert the speech into text. And you have a speech synthesis in the end to try to convert the text back to speech. So basically, so your agent can talk to your users. And the second module in the line is a so-called language understanding component. So you will take the raw text in and try to convert it into a set of symbolic representations. So this representation is usually defined by developers. So you can, in Dialogflow you have so-called intent and entities, and you want to create these kind of definitions, and then you have a model to learn to map the text into the semantics. So the notation we use here is called dialog_act. So you can see that there's a dialog_act type called inform combined with a bunch of sub-layer pairs, which is the entities. And then once you have this, then the next module in line is the so-called dialogue management. So usually this part will take over the semantics, try to figure out the query to query the third-party APIs, For example, if you are building a chatbot for accessing, for book Uber, you actually need to go to Uber's API surface and check whether there's a driver nearby or not. So basically, once you have this, you can condition on what the users say and the result from a third-party API. You can have you can feed this into a. So basically, you will have an agent to do a decision making based on a system act, and then based on the system act, you can have a generation to realize it into text. So basically, this is an entire infrastructure of a conversational AI. So you can see that there are lots of different system components there require different kind of technology. And each of these actually requires a lot of time to actually be an expert in it. And then so these components has two particular problems. One thing is that these dial-up notations usually is not very hard. It is not very easy to understand by normal people because you need to define the semantics, and then this is usually you need to teach each individual person to get to know it. So in this case, this is not very easy to be annotated. And then another thing is that so then why we want to use machine learning to solve this? You can think of like machine learning. For some of you probably don't quite understand what machine learning is that basically it's a collection of models that can summarize the massive work for you. So as a developer, you can think of machine learning as a new way for you to program your machines. It allows us to program the machines with examples or data. Right? So basically, imagine you are a developer. You just need to sit there and write down a bunch of test cases so that you can have a model to figure out how to do this logic for you. That's good, right? So basically, it's a way for you to find an optimal solution autonomously by defining the objective function, and then you can just let the machine to learn it. But so you can imagine that as a developer, you're sitting there coding out all the logic of this, but as a machine learner, you may imagine yourself just press the button and waiting the machine to give you better result. But usually it's not that easy, so there are quite lots of pitfalls in machine learning. So here are the three pitfalls I want to talk about. The first one is don't be an ML fanatic. So basically, you need to realize that ML is very powerful. It can actually allows you to do a lot of things, but it's not. You cannot rely on it to do everything for you. One very important example is that, for example, sorting an array is very easy. It's very easy to call out, but it's actually very hard for the machine to learn. Okay, so focus on learning everything. Focus on learning all the system aspects will lead you nowhere. So end-to-end learning nowadays is very popular, but don't think about that too much because usually in the production time, it's not very pragmatic. And you need to treat ML as a tool for solving the right kind of problem instead of solving every problem with ML. So one example is, I want to give an example, is this sequence-to-sequence model. So now in the Google translation, they actually deployed this sequence-to-sequence model for machine translation. So this model is a very good model for translation problem because it's a well-defined problem. Once you want to transcribe English into French, there's only very limited amount of sentences that actually can match to your answer. And you have, when you apply sequence-to-sequence models, which is a neural network-based models, you have a lot of parameters and you just fit it with a lot of data. You can learn very well. And a very important characteristics of this problem is that the input-output usually have a very strong concurrence relation. So you have, for example, you say I'm a student. When you want to translate student into French, there's only a few kinds of words you can use in French. So the concurrence statistics is very strong. And this end-to-end learning can actually help you to remove a lot of these intermediate states, so you don't actually make errors. don't make compound errors. But if you apply seek-to-seek for chatbots or conversational agent, it's actually not easy. So you can see, like, because chatbot is actually a very obscure problem. What is a good behavior of a bot is not well defined, right? And then usually, if you want to build a conversation agent for a particular business, usually if you use this end-to-end learning kind of approach, you will actually couple the language with the business logic. But a lot of times, this business logic, the clients want to control themselves. So a lot of times that you end up learning something your clients probably don't want. So it's a problem. And also in the data itself, it has an end-to-end, one-to-many relation between the input and the output. So usually given a single input, you can actually, there are several different ways to reply to that input. So in this case, the model will struggle to learn a very general behavior. So in the end, a lot of these sequence-to-sequence chatbots, the behavior it learns is just to say, I don't know, or I don't care to every reply, because this is the safest choice for it. So another example I'm going to give is using the DeepRL example. So a lot of you have known that DeepMind actually did a very good job in training a Go system from scratch, just using reinforcement learning. So a lot of people started to think, yeah, this is a good idea. Why not apply this to my own problem? But although it goes quite far, anyway. So although Go seems like a very difficult problem, but if you think about it more carefully, it's actually a very well-defined problem. So for machine learning, it's more about whether the problem is well-defined or not, rather than whether it's difficult or not. So for example, Go problem, you have a very clear reward function. In the end, you can just judge whether this system is good or bad by give a win or loss reward function. And you have a finite number of actions, that is the next move, right? Although the action set probably is still very big, but it's a finite one. And then you have a finite state of configuration, the states, right? So this is basically the 19 by 19 grid. So the state action are well defined, the reward is also well defined. So this problem is very good for machine learning to figure out. But for chatbots or conversational agents, the story is different. Right? If you want to apply reinforcement learning, the first thing is, what is the reward function? And the reward function is actually very ambiguous if you think about it. What is a good agent behavior? Is it about to get my task done, or is that actually need to care about whether I'm satisfied or not? Whether the conversation is actually natural or not, like a human or not. So there are lots of aspects there. And then also you have an infinite number of actions because your output is a natural language. So you need to actually do a lot of things to summarize it. And you have an infinite number of states as well. So yeah, again, you need to somehow summarize it. So a lot of caveat here when you apply DeepRL to a different problem. Then the second pitfall I want to quickly talk about is runtime. So users, when using the products, they are usually looking for seamless interactions. So your runtime needs to be very, very good. But academia usually ignores that. And so sometimes it could be very hard to flip if you come from academia. So quoting our software architect, he says that a very simple model can are usually better for deployment and quick iterations. So I will give you an example here. This example is the Google Smart Reply. So if you don't know Smart Reply, now that if you open your Gmail in your iPhone or Android phone, now in the button of your email, you will get 3 buttons that suggest how you can actually reply this particular email. So in the original smart reply, what I do is a ranking-based model. So based on a bunch of a bunch of responses in a white list, they are using a sequence model to rescore about this set of sentences and choose the most reasonable ones. So you can see that you are using an LSTM model for sentence scoring, which is a very complex model. And then basically inference is done by organizing the response as a try and do a bin search over it. So one of our scientists, Matt, when he did his job in Google, he actually helped to improve the smart reply quite a lot. So what he did is actually using a very simple model. So basically you can just using a so-called dot product model. So first of all, you can actually encode all the responses first into vectors. So this can be pre-computed, pre-processed, right? And you just put it there. Once a new email comes in, you encode the email into vector, and then you do a dot product between the two vectors. And then you can do some kind of hierarchical quantization for search. And the result, when you compare the C2C plus bin search and the dot product plus the hierarchical search, you can see that the conversion rate, which is the performance of the system, is actually considered to be 5% better by the human users. But actually the speed, you can speed up 100 times more. So you can see that very simple, your model doesn't need to be very complicated. You can just have a very simple model reach the same level of performance, but with like 100 times faster runtime. Right? So the second important thing is data, because data is so important, so we need to say it 3 times. Okay, so data is a core of an ML algorithm, right? So one of the reasons why deep learning can took over in the past few years. And data, so that's why data should be also a core of an ML company too. So if you are running an ML company, make sure you own your own data. You have a way to generate your own data, and you have a way to label your own data. So you can actually make use of them, okay? So just to echo this aspect, this is the importance of the data diagram. So these blue line are the speech recognition. So if you look at the speech recognition in the early 20s, you can see that when the first hidden Markov model was proposed, it was in 1984. So this is basically an algorithm breakthrough. But once you have an algorithm breakthrough, you need to wait for a very long time until a very good data set is first released. So in this case, it's a Wall Street Journal corpus released in 1991. And then after that 3 years, you can reach the human level clean speech ASR. Another example is machine translation. So the first statistical machine translation method was proposed in 1988. But it only waits until Google released their web and news page corpus in 2005. And at the same year, they declared that they have the Arabic and Chinese to English translation system. And the next example is image recognition. So for convolutional network was first proposed in 1989. So nowadays, we need to wait until the ImageNet corpus is first released, and after 4 years, we can reach the human level performance. So the same thing is the same for demise Atari games. So when the Q-learning was first proposed in 1992, and then only like in 2015, they just reused these Q-learning methods plus a lot of data to actually reach a human level control. So basically, the summary is that when you have the first AI algorithm proposed, you will expect to have you need to wait for about 18 years to actually reach an AI breakthrough. But if you have a very good data available in that domain, it only takes about only 3 years for you to actually reach the next milestone. So that's why data is so important. And conversational data is also usually very hard to get. So people can say that Reddit has a large volume of conversational data. We can use it to train the chit-chat dialogue systems. but usually it doesn't work that well. So, but we can ask what if you want to get a domain-specific data set, right? Then, for example, pizza delivery agent or taxi booking bot. Do we want to just grow it from web? I don't think so. You should just collect your own data, right? So in the past, in our PhD, we actually proposed a new framework for collecting data called Wizard of Data Collection. So the idea is that instead of that your user talking to a system, you actually put a human behind it. And then you give the human the access to your database and all the interface that is required to perform a task. So that you let the two people talk to each other, and then you can just log down all the conversations, and afterwards you can use a model to learn from it. So another data collection framework proposed was by Google in actually this year. So actually their approach is that they design two agents and let them talk to each other at a semantic level, and then try to use some of the templates to generate template sentences, and then afterwards ask the turtles to rephrase the sentence. So you can get a natural dialogue. So basically the key takeaways here is that so the three things. The first thing is that be programmatic, don't be an ML fanatic. Identify the problem. What is the thing you actually need ML to solve, and then you solve it by ML, right? And be aware that oftentimes simple solutions could work far better than complex solutions. Although complex solutions usually is better for you to publish a paper. And then you need to collect and own your own data. Okay? So talk to us if you are interested or curious about PolyAI.